Okay, so our final topic is oscillations. And oscillations are big because they're a new type of motion to look at. That we can use the same analysis we've developed all semester to look at oscillations, but they're kind of a different type of motion. And Physics 2 starts directly after this chapter in chapter 16. So you need these skills from this chapter to effectively move forward in Physics 2. All right. So when we think about oscillations, we want to think about motion that repeats. So you can have something like the obvious thing to look at is probably a nice sine wave, which I can't draw. But just because you're repeating doesn't mean you'll be what we'll call simple and harmonic. You can also have square waves, right? So you'll notice the difference between, oh, that was wrong. I have to take this out. That's not a function anymore. All right, so there's all sorts of ways to repeat and be periodic. And we're going to look at repetitive types of motion. And this will help us get into wave motion. Now, of course, I can't draw this nearly as well as I would on a blackboard. Let me try and draw a nice wave. This is why we really need the. Yeah, I'm not even gonna continue that. That didn't work. So let's talk about. First, what I want to do is I want to actually look at some pictures of what I'm talking about here. So you can see we're going to define a motion called simple harmonic motion. So you'll notice we won't look at the sawtooth or square waves. We'll look at nice sine waves because sine waves are both continuous and smooth. All right. If you look at a sawtooth wave, right, it's continuous, but it's not smooth. Right? You have these points that are not differentiably smooth. And square waves are not even continuous. Right? They're periodic, but they're not continuous. We don't want to look at those situations. We just want to focus on something that looks like this nice continuous sine wave. But before we get back to talking about simple harmonic motion, we need to define some of the terms that will be important to understanding harmonic motion, and we'll formally define simple harmonic motion in terms of the things we just discussed. All right, so let's take a look at some of the terms and items we will use. All right, so first of all, we're going to be talking about periodic motion. So periodic motion repeats. So therefore, it will have a time in which it repeats. And it will also, I don't think we have wavelengths here, but it'll have but when you look at something, right, there's the time it takes for one complete cycle. That's called the period. And then the number of cycles per second, right, is the frequency. So I don't know if you can hear, I'm going to tap on the microphone. It might be a little obnoxious, but that's a low frequency process, right? That's a high frequency process. It's happening more times per second. So so the unit of frequency is named after Heinrich Hertz and is abbreviated as the Hertz. And remember, frequency is 1 oscillation per second, and it's defined this way so that 1 over the period, or 1 over the frequency, is the period, and vice versa. Right? You can do that pretty easily. Now, any motion that repeats regularly is periodic. We saw that with the square wave and the sawtooth wave just in the last slide we went over. But simple harmonic motion is not only periodic, but it's continuous and differentiably smooth. All right, so it has these it has these extra criteria, and it is expressed in this way. All right, so let's talk about what each of these are. So because we have a cosine function, a lot of the terminology from your pre-calculus days will come back. So x is the position along the harmonic motion. All right, xm is the amplitude, and omega t plus phi is the phase. Okay, so the amplitude tells you your maximum displacement. This is how far away you can get. So when you're looking at a problem or something like that, if it says it's stretched to a maximum distance of 5 centimeters, that's your amplitude. All right, but you'll notice all the time stuff is here in your phase. And we have a little bit of an issue here, because you'll notice we have an omega. All right, this omega is doesn't really work in the same way omega has worked for rotation. Although we'll still call it the angular frequency. We'll call it the angular frequency, we won't call it the angular velocity. So this omega is equal to 2 pi f and is a fixed part of the harmonic motion. This omega is not equal to, well, it can, I suppose, be thought of as d theta dt, but that's incorrect because it's not really a dynamic quantity. What I mean by that is once you have simple harmonic motion going on, we're only going to look at simple harmonic motion with one frequency. Even when we damp it, that'll only affect the amplitude. We don't really change the frequency. So whatever motion we're looking at will have a fixed frequency, and then omega will be a part of that simple harmonic motion. It's angular frequency, if you will, not really defined as d theta dt. So you want to be careful there, because we're starting to really overload some symbols. So context is everything. Oh, I should start a video. Sorry. All right, there I am. So going forward, we can see a particle oscillate from one side to the other. Now, you might wonder, well, why sine or why cosine? Typically, it depends on the boundary conditions. If the sine function certainly can be used for simple harmonic motion, but typically when we physically look at something, we have to ask ourselves, are we looking at the whole picture, or are we mechanically starting the system? You'll find that when you look at sort of a whole picture, both back and forth, like for an electromagnetic wave, say, the sine function is what you'll use. Because at 0, well, you want everything to be 0, because it's not really, you're not really mechanically moving that one way or the other. The light is just the light. However, when it comes to mechanical motion, usually you get something moving in simple harmonic motion by pushing it or pulling it from its equilibrium position, sort of like a spring, and then letting it go. So you're usually starting at your amplitude, and if that's the case, then cosine, because cosine of 0, right, will give you that amplitude. So let's take a look at that function again, so you can see what I'm talking about. So xm is our amplitude, and we have times cosine omega t plus phi. So phi is like your constant of integration. So we'll usually set phi equal to 0 unless otherwise stated. Okay, so if we do that, then this function above becomes x of t equals xm cosine omega t, right? And so at t equals 0, x equals x of m, which is just your maximum displacement. All right. So as we go through, you'll notice, again, the same thing that I just said sort of mathematically up here is illustrated graphically here. We start here at the top, and we cycle through. You'll notice that you have to get back to not only the point you started at, but then moving the same direction afterwards, right? So for instance, one might think, well, wait a minute, we crossed 0 twice, isn't that a period? Well, here you're going down, here you're going up, so that's not a period. You'd have to wait to look at a period from 0 here. You'd have to get back to over here where the particle will cross 0 and be decreasing again. Okay? So now, since we have x, we're going to do the same things we've always done, right? Which is that we're going to want to find v equals dx dt, right? And a equals dv dt. So let's do that really quickly, okay? So as we can see here, we've got v equals d dt of xm cosine omega t. So xm is constant, so that will equal to minus xm omega sine omega t, right? We just take the derivative of cosine. And remember to use the chain rule, that's where that omega comes out. And a, we can take the derivative again. And so if we take the derivative of that guy right there, we get minus xm omega squared cosine omega t. All right? So, things to notice. A equals minus omega squared, right? xm cosine omega t. And you can see here that A equals minus omega squared x. Fascinating, yeah? So, that will have some interesting consequences. We can then apply Newton's second law once we have that. So if F equals ma, right, we have F equals m minus omega squared x. And if you recall, omega is equal to the square root of k over m. So m omega, if you square both sides, you get k is equal to m omega squared. And you can see here that F, if we're looking at a spring, will equal minus kx. So we've actually now just derived Hooke's law. Try to make that an underline. Okay? So we can see that we've already sort of looked at a case of simple harmonic motion, which is the motion of a mass on a spring. And we've certainly been able to find out things about it previously by solving for Hooke's law, but now we can see that Hooke's law is simple harmonic motion because its trajectory, as we've shown, an object with that trajectory, we can sort of plug it in and get that expression right out. And what I want you to see here is that all we've done is taken a new kind of motion and put it into the same use the same definitions to analyze it. All right. Now, what you'll find is that we'll also talk about energy associated with simple harmonic motion, so we'll sort of do that part of the course too. But if we were to go into fluids and gases, which we unfortunately won't have time to do, you do the same thing. You really just create the equations that allow you to look at the velocity and acceleration of a fluid and apply Newton's second laws. And then you get all sorts of interesting things for fluids. You get to talk about flow. And then for gases, you start to get things like the ideal gas law and things like that. So you really are breaking up mechanics into solid, liquid, and gas. And we're really sticking to solid here. But again, those chapters you should be able to sort of, if you need them, you should have the book and be able to look at them on your own. Okay, so let's move on. You'll notice that they break down everything here that we've already talked about. So this is a good sort of summary to say it again. So looking at the anatomy of simple harmonic motion, we can see we have the displacement, T, right? This is just the value at any given point along that curve. Again, the amplitude is the maximum value. Now you'll notice this part is the phase. So you have the angular frequency, the time, and then the phase constant. Like I said, we usually set this equal to 0 unless otherwise stated, but this just moves the trigonometric function back and forth on the axis, right? It shifts. And it'll adjust for the initial conditions for t equals 0. That's a good point there. The only thing I'd want to keep in mind again is that the angular frequency omega, can't say it enough really, is equal to 2 pi f. So if you know f, you know omega, and vice versa. Now you'll notice, one thing to notice that is, I don't know if we've really covered it, but you'll notice that omega has units of 1 over seconds basically, and t has units of seconds, and then you just have radians, you have unitless quantities in the cosine. Always keep in mind when you have to evaluate something in a function like this, it has to be unitless. All right, you have to put that, multiply it by something so that it's unitless. Otherwise, things kind of get all crazy. Arbitrary units are a thing, and that are units that you assign so that everything remains unitless. And then you have to transfer back. Okay, so let me see. No, it's just so if we look here, the angular frequency has this value of 2 pi over f, but you'll remember that with omega equals 2 pi times the frequency, f equals 1 over t. This goes two ways. T equals 1 over f. So don't convince yourself it's one way or the other. These are both true and they imply one another. And so what we can get there is that omega is equal to 2 pi over t. So once you have the frequency, you also have the period. Now looking at it graphically, the period is just the time it takes for one oscillation. So you'll notice on the blue line here, we have blue and purple. So for the blue one, we go all the way here. We have one period here, and the purple one has a higher frequency. So that one will get to the period up here. You'll notice that's mentioned. When you look here, so these two waves have different periods and therefore different frequencies, but they have the same amplitude, right? They both go up and down. So the wave here has two different amplitudes, but the same frequency, right? You'll notice that if I go to one peak, peaks there, and the same thing here, even though they have different amplitudes, all right? So I'm hoping you can visually see the difference between amplitude, and we're sort of modulating the amplitude, right? That makes your wave bigger, and modulating the frequency. That will determine how many periods you have in 1 second. Okay. Now the phase does just what I told you. It just shifts the entire function rightward. So the negative value shifts the cosine curve rightward. You should remember that from Math 200. And so for phi equals minus pi over 4, you have the unshifted curve. This is where phi equals 0 is in the blue. And in the purple, you have phi equals minus pi over 4. And notice everything just gets shifted. You're just translating the function. Okay? Okie dokie. Okay. So I want to be sure I did this with answers. So before we look here, let's do the checkpoint, but what you can see is they're just covering the stuff I covered about velocity. So we've already seen this, but you can see here that we have the correct form, and more importantly that the amplitude of the velocity is omega xm, as we saw when we derived this equation in the previous slide. All right, so again, all you're doing here is v is equal to dx dt. That's it. That's how you get this. Okay, so let's look at our checkpoint and see if we can figure out some simple stuff here. So particle undergoing simple harmonic motion of period t, as like we just saw, is at minus x of m at t equals 0. It is at minus x of m. Is it at minus x of m, at plus x of m, or 0, or in between negative x of m and 0, or between 0 and plus x of m when a equals 2 times the period, 3.5 times the period, and 1.5 times the period. So let's make a simple drawing first. All right. So we're going to say at t equals 0, we're at minus x of m, right? And then let's call that the period, right? So that's it. That's at t, right? That's 1.0 t. So what positions will we be at for 2t, 3.5 t, and 5.25 t? And I want you to notice that your answers should be, there's one, right? Are you at one of these three positions? And then you have these two between answers, or between 0 and positive x. Right, so 2t would be 2 times the period, right? So this is t. I only drew one period for you. And this is minus. So I drew the shape nicely, but I did not draw it symmetrically. I apologize for that. I'm going to ask you to believe. No, it did not draw my M correctly very well either. So basically, where are you along here? Are you at x of m, 0? Hold on, I didn't realize that. Are you at x of m, 0, plus x of m, or in between? So let's take a look. We can always sort of project this forward. So for any integer period, right, that's going to bring us right back to where we started. Right? So anything, so whether we're at 1t, 2t, 3t, 4t, 5t, that'll bring us right back to where we started. So for A, where it's going to be minus x of m. Okay? Now, for a half period, well, for a half period, right, you'll notice if we go to 0.5t, that brings us from, that's halfway between 0 and the period, right? So that'll bring us all the way up here. Okay? So now, because it's periodic, you just, you have 0.5t, 1.5t, 2.5t, and 3.5t will all occur at x equals the positive xm. All right, and you'll notice the quarter periods, both for 0.25 and 0.375, occur here. So because it's periodic, and what I mean by periodic, if you're not seeing it, is it extends indefinitely out like this. I just can't draw it very well. So you get the idea, right? So it doesn't matter what the number is here, as long as it's 1, 2, 3, 4, or 5. If it's 0.25 or 0.75, you will be at 0. Okay? So does that make sense to everybody? Take a look back and understand that you're repeating the motion over and over again. All right? It's not just one hump. It repeats itself. And for our purposes, it repeats itself indefinitely. Okay. All right. So let's go on. All right, good. Now again, we saw this. We saw these values. We derived these earlier, but by taking the correct derivatives, you can see we get the same conclusion that we developed before. We just saw it a little more explicitly, and we can see pictures here, right? So we'll notice that what we have here, this is the, even though we have all those equations, we already derived those equations and understand where they come from. What we want to really focus on here is given a displacement function, right? We want to look at the velocity and acceleration vectors. Now, even though the acceleration and position are related to each other, you'll notice you do have this minus omega squared x. You have a minus sign here and a different scaling factor for your amplitude, all right, than your x function. So even though they are proportional to each other, you'll notice that they very much look different, okay? Because even though it's sort of an inverted function, right? So if a starts at plus x, or if the displacement starts at plus x, as given here with this just sort of nice simple cosine function, the velocity will start, or the acceleration will start at minus omega xm, omega squared xm, right? It'll start on the bottom. And you'll notice that when this one reaches its lowest point, when the displacement reaches its lowest value, or on the negative side, you get a maximum here. So these are just inverted. You'll notice they both cross 0 at the same place, because 0 inverted is just 0. But you'll notice the velocity does follow that sine function as well. Okay? So you have pictures to go with your new functions about the dynamics of simple harmonic motion. Okay? So, this is, again, it's sort of giving us our generalized spring constant, but that's okay. So which of the following relationships between particles' acceleration A and its position X indicates simple harmonic motion? This is an important one. So I want you to recall the relationship A equals minus omega squared X. All right? And which one of those indicates simple harmonic motion? So I've got C. C looks pretty good. A, you'll notice, A is proportional to x squared, so that's not going to be good because it has to be linear. Here it's proportional to x to the minus 1, so that one's not good. What about B? What's wrong with B? The sign, very good. You have to have the opposite direction in order for it to go back and forth and have that periodic periodicity. If there's no minus sign, it's just going to keep going faster and faster and faster with position. So B is not correct either. Only C will give us the simple harmonic motion. Okay? So again, we have more of just, oh, did it ask for the angular frequency? Oh, for the y, what's the frequency? You just take the square root of this part and get the angular frequency of 2. It's not so hard. Oh, it's starting to rain, I think. Yeah. So you'll notice that that we just sort of have slowly been deriving the stuff we did on that big slide where we saw everything from Newton's law. All right, so we saw it quick and at one time, and now here we're just sort of slowly getting there. And again, we saw this before. You can set MA. You can replace A with minus omega squared x, and they've isolated this part here. And for linear simple harmonic motion, F is proportional to x to the first power, that is, gives omega equals the square root of k over m, and the period equals 2 pi over mk. You can derive the period function from omega, right? Because remember, omega is equal to 2 pi f will equal the square root of k over m. So here you can just say, okay, I want to solve for the period, so that's 2 pi over t equals the square root of k over m. And then you can multiply by t, invert, and you get 2 pi m over k, right? Just by multiplying it on the other side, and that's going to equal t. So with simple algebra, you can derive one from the other. But we already saw how to derive this using Newton's laws. It was pretty straightforward. Right? Okay. Yes.
When we say K, does that mean the oscillations are about like the spring forces, or it could be any force?
Well, K, when we look at, it's a good question. So K in this sense, I mean, for a spring, K is the stiffness of the spring, right? And can be looked at this way. But we haven't really restricted ourselves to a K yet, and we're going to find, for instance, with pendulums, that omega is going to look a little different. We're going to find it depends on gravity and the length of the string, for instance. So right now, even though we'll be able to use the same relationships, but we'll get different realizations of this K and omega. All right. So
that makes sense. Thank you.
Yeah. Okay. So now let's look here. Which of the following relationships between the force on a particle and the particle's position of x gives simple harmonic motion? All right. So I think we're in the same boat that we were before. So it should be easier this time, right? Oh, it's not rain. That's just pigeons. I hate the pigeons. All right. Okay. So remember, F has to equal minus kx in this case, right? Good. So A clearly satisfies the conditions. F, B, x is not linear. F, there's no negative sign, or for C, sorry. And D, again, there's not x. So there's only one possible answer, which is A. All right. So I am teaching 231 in the fall. I just submitted the names. They should be up there, but I am teaching, I believe, the evening course. Let me check really quick. Yeah, I'm teaching the evening SCP-232. All right, so now that we've done the dynamics of simple harmonic motion, we get to do the energy. And again, everything in this chapter is really crucial for Physics 2, because we'll see this in when you talk about inductive circuits and AC circuits, you will be looking at oscillators, the energy of oscillators, and that will be critically important. And also the nice thing about oscillators, energy of oscillators, is we can sort of see how to form equations of motion through energy as well, which we can look at here coming next. Well, I don't know that they just stick what works with your schedule. I don't know that they match you with specific professors. The morning course is that's a whole other issue. So we need to write the functions for kinetic and potential energy. So again, we want to roll back. We want to go back to the things we know, right? Which is that K, kinetic energy, big K equals 1/2 mv squared. And we know that for a spring, for instance, U equals 1/2 kx squared. You're going to notice, though, that instead of being constant, these are now functions of time. So we have to plug in, we have to square x, so we have to square both the x of m and the cosine omega t, and we have to square the velocity function. You'll notice that'll make the minus part go out. But you'll notice that when we define things this way, right, we can get the same amplitudes for K and U. So let's take a look at that. All right, let's see if we can make sense of that. So let's see. We believe that with K, with UT, this makes sense, right? But with V, with K, we have 1/2 mv squared, which is going to equal 1/2 times m times minus omega squared is going to be omega squared. xm squared is just going to be xm squared. And then we're going to have x was cosine squared omega t. We can even keep the plus phi here, it doesn't matter. So what you can see here is that you have, if you remember, K is equal to m omega squared, right? So this part becomes K, and you indeed recover 1/2 K xm squared. Why is this so important? Because when you add the energy, you have the same amplitude for both, and sine squared plus cosine squared is equal to, of the same phase, will always just be equal to 1. So that lets you see that the total energy is actually conserved and is constant, right? That's something we expect. We expect the total energy of a mechanical system without friction or loss to be constant. And we get that result. So our energy is consistent, like we would look at it, and is conserved, and we can look at the energy diagram here. You'll notice you have this nice constant energy line up top, and you'll notice that you can, when you start off with one energy, the kinetic, well, let's see which one is which. So this is, the green is potential. So you can see that the potential will oscillate, and as the potential decreases, that gets turned into kinetic energy. And that's when you lose all your potential energy, you have maximum kinetic energy, and vice versa. And you go all the way through. And you'll notice when you add them up, you get this constant line. Now, this is actually a really interesting technique because what you're doing here, and you see this in math sometimes, but energy lets us take advantage of this sort of incredible technique, which is that if one thing is easy to find, right? Say there's two, you have to find the kinetic and the potential energy. Say one of them is easy to find, which is usually the kinetic energy, and the potential is hard to find. Once you find the kinetic, if you can restrict your system to be lossless, then you need not actually find the potential, right? Once you draw the kinetic energy, you can just say, well, whatever this is, this must obey the rule that the potential plus the kinetic has to equal a constant value. So you can find your maximum kinetic and go from there and start mapping your potential energy. And this is actually an incredibly powerful technique because it's not always trivial to derive these potentials or to get them or to express them. Sometimes because of energy conservation, all you need is one, and then you can get the other automatically. Okay. So you'll notice we have a spring. We've got the equilibrium position. I just want to remind you of some basic spring stuff. We've got our equilibrium position, right? If we start at equilibrium and let the spring go, it'll stay at rest. And then we have our amplitudes based on, what we see with springs. So that should hopefully make the simple harmonic motion make a little more sense connected to a physical system. So in this figure, 15.7, the block has a kinetic energy of 3 joules, and the spring has an elastic potential energy of 2 joules. All right, when the block is at x equals 2.0 centimeters. What is the kinetic energy when the block is at 0? What is the elastic potential energy when the block is at b, negative 2 centimeters, and c, negative x of m? All right, so remember the whole thing here. First of all, you want to ask yourself, what's the total energy? E. E equals k plus u equals constant. So you want to look at this and sort of create your own energy diagram and figure out what the energy will be at each of those points. Okay? So my pre-question to you that I'm going to answer is, if you look at this, you can ask yourself, well, is 2.0 the amplitude? Is it one of the amplitudes? So would it be the positive amplitude, or would it be in between 0 and the positive amplitude, or 0 and the negative amplitude? Well, since it's positive, we know that it will either be between or at x of m. But we can see that there's some kinetic energy and some potential energy, right? And when the spring is fully extended, there is no kinetic energy. What's the velocity when the spring gets to x of m? It's 0, right? And so if it's 0, that means kinetic energy is 0 and all the energy is potential. So you should be able to see that plus 2 is between 0 and plus x of m. So with that in mind, I'm hoping that the 3 questions that are asked here are simple. So I'll give you a couple minutes to work on those. Anyone got the answers? Okie dokie. Well, okay, let's take a look. Let's take a look. So it wants to know what is the kinetic energy when the block is at 0. So here we have to understand, right, that the block at 0 has maximum. So at 0, E equals K plus U, but U is going to be equal to 0 here because that will be its maximum velocity, right? And we can tell that also because U equals 1/2 K X, right? And here X is equal to 0, so U is equal to 0. Okay? So the kinetic energy at X equals 0 should be equal to the total energy, and the total energy will be 3 plus 2 equals 5 joules, right? And that constant, that energy is always constant. You can find the total energy at any point. So good. So I think you got A5, good. And then let's see. So what is the elastic potential energy at X equals -2 centimeters? And at C, X equals minus X of M. So C is the easy one, right? Because at minus X of M, we know that K will equal 0. So U must equal 5 joules. All right? Because they asked for the potential, the elastic potential energy, right? So it's not going to be 0. And then at -2, right, we should have, we should be able to see that 1/2 kx squared, right? You'll get the same value whether x is equal to 2 or -2 because you'll square it. So the potential energy should be the same as the one that's given, and the elastic potential energy should be 2 joules. All right, so let's do our sanity check. Right, 525. Okay, recall that we did C first. That's why it seems out of order, because that one was easier. Yeah, Mina.
Sorry, I just want to confirm. For C, and the position minus XM, how did we get again the 5G? Because is it 5G? Isn't supposed to be essentially the total kinetic the U?
Remember, E is always equal to K plus U, period.
Correct.
Right?
But in minus XM, that doesn't have kinetic, right? It has only potential.
Right. That very good. So we know here that the total energy is 5. That can't change. So at the maximum position, right, it doesn't keep going forward, so it has to stop and then start moving the other way. So if it stops, that means its velocity at xm or minus xm is equal to 0. If its velocity is 0, its kinetic energy is equal to 0. So E equals U equals 5.
Oh, I see where I got confused. Okay, got it. Okay, thank you.
No problem. It's a good question, Mina, because I've got to tell you, in my years of teaching this class, there's a lot of confusion around sort of adding these things up, particularly because the energy stays positive even though the position goes negative, and you just got to keep adding it up and seeing that the energy conservation applies at each and every single point along the way.
That is correct. That's one thing that is confusing. The other one is the all-time favorite error we do when we don't really read what we have in front of us. So I was reading 3J and 2J at x equals 2 centimeters. For some reason, I was not seeing the 2 centimeters. That info is not within my radar.
It happens. And I gotta tell you, it's honestly, it's better to see it in a checkpoint than in a test, right? So So read those problems carefully. But it happens to me too. I mean, you'd see it probably more. Well, no, you've probably seen it a couple times in even this semester where I get lost in a checkpoint, and it's always because I didn't read it carefully. Almost always. So you should see that it's something. It's more like discipline, right? It's like learning a martial art. You have to just be disciplined and read the whole problem to go through it. And no matter how experienced you are, even if you do this for 2 decades, if you don't read the problem, you will get lost.
All right. Thank you, Professor.
You're welcome. So let's take our break. It's 2 o'clock. We'll come back at 2:15, and we will talk about pendulums. All right. I'll leave the answers for this up so you can study it though instead of going forward. So I'm going to be away for a couple minutes, and then we'll start at 2:15. I'm back. So something I wanted to write down and show you really quick before we move on is that we have F equals MA equals minus KX, basically, right? Now, another way to write this is we can write M and yet another way to write this is and this is a second order homogeneous differential equation, and you'll find that that is the harmonic oscillator equation, or the equation for harmonic oscillation. So this is an ordinary differential equation, and in the next level or intermediate physics, this is how you would describe the motion. And then when you solved it, your answer would be that x equals omega t. Okay? So we're going to see this when we talk about damp motion at the end of the chapter. That will make this a little more complicated, and we'll see how that happens. But until then, we want to switch to our main application, which is, well, pendulums. But we want to look at we'll sort of build up pendulums by looking at angular simple harmonic motion. All right? So what you're looking at here is what's called a torsion pendulum. All right? And if you can see my pen here in the if you imagine my pen is attached. Well, no, that's not going to work. Well, let's use a Snapple bottle. You see this Snapple bottle? As I go back and forth, that's the torsion motion. All right, so the string would go back and forth and twist. You get to interesting things like tensile strength, things like that. But that's your torsion motion, and that's what's going on in this picture here. Right? You can see it's going back and forth like that. That's the equilibrium position. You have a theta amplitude of plus theta and one of minus theta. Now, let's take a look at our equation for the period. You'll notice that to make it angular, right, it moves in simple harmonic motion, not so much with a force equals kx, but with a torque of minus kappa times theta, where kappa is called the torsion constant. And this is an angular form of Hooke's law. So because it's an angular form of Hooke's law, we can replace m will go to I, and k will go to kappa, sort of the script k. And so when we do that, you'll notice we very readily find that our period will be equal to 2 pi times the square root of the moment of inertia over the kappa constant. Okay? So that is the period for a torsion pendulum. And we'll sort of continue. You'll notice that if we look at a simple pendulum consists of a mass, or a bob as it's often called, suspended from an unstretchable massless string. And the bob feels a restoring torque. You'll notice it's still undergoing itself in angular motion, similar to the torsional pendulum, but a little different. And the restoring torque will be equal to minus L times Fg sine theta. And that, of course, you'll recall from, we're not inventing anything here, R cross F, right? There's your R, F, but it's restoring. That's where the minus sign comes from. You can sort of see it diagrammed out here. Okay, we have the force of gravity. You have L, your tension along this line, and that it will reveal the torque, pulling it back the other way. So relating this to the moment of inertia, we can get this expression for the angular acceleration. mgli times theta, not sine theta or anything else like that. You'll notice that again here, the angular acceleration is proportional to the position but opposite in sign, just like it should be for the linear case. All right, that's emphasized here by this minus sign. Going forward, we can see that the angular amplitude for theta m of the motion must be small. Now let's go back and take a look at that. All right, so if theta is big, then this becomes, this can get out of hand very quickly and become nonlinear. So your pendulum, simple pendulum, only has simple pendulum motion for small angles of theta. Now, you can actually have fairly big angles of theta for a single pendulum, but if you were to add another bob, say here, and have another pendulum of mass m, this gets nonlinear very quickly. And there's some pretty interesting stuff on the internet if you look at double pendulums. I might send you a link on that next week. Okay? So, we see that that has to be true, and the angular frequency will be mgl over I when theta is small, and the period, so if I equals ml squared, we can see that omega will be equal to the square root of g over L. So you'll notice that the frequency, a few things here. You'll notice the frequency actually doesn't depend, because we have the moment of inertia down here, it does not depend on the mass. So whether you have a bowling ball or a little marble, you'll still, it only depends on the length of the string. If both those strings are a meter in length, you'll have the same frequency, whether or not it's a little tiny mass or a big mass. And you can see that if omega is equal to g over L, you can get the period is equal to 2 pi L over g, solving the same way we did before. Oh, now it's really starting to rain. So physical pendulum, you can think of like a bowling pin or a piece of cardboard. You'll notice you have your center of mass and a point around it here. It has a complicated mass distribution, so they can be a little harder, but the period will be given. You can do a similar analysis to get this period, where I is the moment of inertia. So I, of course, is particular to the mass distribution, and length, rather than length, this h is the distance from the pivot point to the center of mass. A physical pendulum will not show simple harmonic motion if pivoted about its center of mass. All right, the center of oscillation of a physical pendulum is the length of a simple pendulum with the same period. So you can see, let's look at the picture of a physical pendulum again. It's something like this. Okay. All right. No, I wanted to show that. So one of the interesting things you can do with a physical pendulum is you can use it to measure G. So this would be a little more impressive had we been in the lab and actually measured free fall. And interestingly, one of the, well, what I say interestingly, because science is kind of done this way, right? It's not enough to have one way to measure G. You want to have a bunch of ways to measure it and see if you get different things. The more independent they are, the better. So you can you can use these spark tracks, which we used to use in the 80s, 90s, and the early 2000s. You can use these picket fences, which were used in the most of the 2000s and the 2010s. But one interesting thing to do, I think, for the last lab, which I may do, is to have you measure the gravity here, and to have you measure gravity, little g, and then with the physical pendulum. And it would almost be fun to have you design it yourself if I were doing that at the end. So a physical pendulum can be used to determine, again, g, assuming the pendulum is a uniform rod of length L, right? So this is how you do it for length L. You would use the parallel axis theorem to get where your new moment of inertia. You could plug it into the period equation you have before, and you can solve for g. And you'll notice that, again, this is how we do science. This is very scientific. There's the thing you're calculating, you're predicting in terms of the things you can measure. All right? So instead of having an elegant math equation that's as compact as possible, usually we want measurable stuff on one side, stuff to measure. We have stuff to predict on the other side. Okay? So I don't think we'll do this checkpoint. I would rather move on. And this is not useful, I don't think, really either. Basically, what they're doing is they're sort of showing that circular motion and simple harmonic motion can be viewed equivalently, and they can. But when you look at circular motion, you're going to get x of t. If you really want to do this correctly, you should write it like this: equals I omega t. That's how you should write the function, where I is equal to the square root of -1. So if you thought the square root of -1, or what they call quote-unquote imaginary numbers, don't have applications in physics and engineering, you would be incorrect. Yes, E. Exponential e to the I omega t, where I is the square root of -1. Okie dokie. So now we'll go to, we'll talk about damped and resonant harmonic oscillators. So the damped harmonic oscillator has this, and this is where fluid dynamics would have come in helpful. It has this damping force where we're damped. So you'll notice that it depends on this constant here and the velocity, right? But remember that the velocity is equal to dx dt, and B depends on the vein and viscosity of the fluid. It's funny, we only mention those in chapter 14. It's not like you become experts in vein and viscosity. I don't think I could tell you what the vein is actually off the top of my head of the fluid. So I guess the vein is this thing here. The viscosity of the fluid is how easy it is to flow through the fluid. But yeah, so you can put something in here like this, and so I guess it depends on the surface area of this object. That would be the vein, and then the viscosity is a property of the fluid. And you put this in here, and you can have it damp the motion. So you'll notice that we started with this term and this term in our differential equation the first time, and now we just have to add the damping term, and we have our whole second order differential equation with damping. And so now we have to find a solution to this equation. Now, when you're solving differential equations, what you'll realize about them very quickly is you'll either need a computer to solve them, or there are some techniques to solve for specific equations of forms, certain differential equations of certain forms. But for the most part, someone has come up with a solution, right? So the solution to this equation is given here. And the first method you will learn in solving differential equations is knowing the answer. So knowing the answer is, you check, you're going to guess that this is the answer, right? So then you find dx dt, which I'll leave you to do because this is all calculus stuff, just simple calculus. You find the first and second derivatives, you plug those into these equations, and then you do the math. And you will find that when you do the math and you put this solution in for each of these three terms, for for x, dx, and the second derivative, you will find that it equals 0. And you'll find that there's a modified angular frequency, right? That omega prime, it still has this k over m term, but it'll have this modification, b squared over 4m squared. Okay? So you will find that when you look at it, you still have the oscillating part. So the frequency changes when you damp it. But I want to go back to what I said earlier, and I hope you can see this, is that you have the undamped versus damped frequencies are different. But once you have this frequency, this damped frequency, it doesn't change even as the envelope, the amplitude decays. All right, see this exponential decay of the amplitude with these dotted lines, but you'll notice that the frequency does not change as you move through and the amplitude gets smaller. Okay? All right. So if the damping constant is very small, then omega prime is approximately equal to omega. And for small damping, we find that the mechanical energy can be substituted by our new decreasing amplitude. So we have this approximate function for our energy. All right. We might be able to get to fluids after all. Because I still have plenty of time, and the only thing I have to cover is forced oscillations. So the opposite of damping would obviously be driving or having a driven oscillation, right? Which is subject to a periodic applied force. You have to apply something periodically, not just constantly. So a forced oscillator at the angular frequency is its driving force. So you'll notice you can drive this. This means you have like a knob, and you can modulate and turn the frequency, all right? And when the driven frequency is equal to the natural frequency, then you're in resonance, okay? So what happens with resonance is that you actually build up energy at a very rapid rate. And if you're driving, again, there's a difference, right? You have your spring system. This has some resonant frequency, right? It's connected to a motor that will make this go up and down, and that has an omega prime dial, omega driven and omega. So I hope you can see the differences between the two omegas. Yes, question?
Yeah. Is it? So engineers, special civil engineers, they keep when it comes down to bridges.
Right.
When,
I was just about the final thing we're going to do today is I'm going to post the link to that bridge collapsing.
Okay, because I was I would love to see a breakdown in physics of this, because we have gone through over it very, on the surface, but it would be nice to actually see it break down.
Well, the physics breakdown isn't really that deep, because but basically it's sort of exactly like this, and I'll it's sort of equivalent to this. So okay. we have our omega of our system, right? Where you can almost think of this as the bridge. And then in the bridge example, instead of having a motor where you can adjust the omega driven, you have wind, right? So the wind represented the omega driven in the bridge, and the bridge, the geometry of the bridge allowed for a resonance to be set up at a frequency that was close to that, that could be found with wind. And then it's just a simple matter of driving it at resonance. So let's actually take a look at that, because that was sort of my what I wanted you guys to watch. So let me just get the link, set the link so everyone can watch it. YouTube. Hold on. Tacoma Narrows Bridge. All right, so we'll watch the 5-minute version. Oh God. So let me go back to you guys. And there should be a link there for you. And you should be able to watch the Tacoma Narrows Bridge collapse. So take a couple minutes and watch that. And I will, and as you're watching it, note that the wind acts as the driver, and the bridge, the geometry of the bridge, the way it was designed, has a resonant frequency. Okay? And all that's going on is that the wind is driving the bridge, the oscillations in the bridge at its resonance frequency, and as it keeps doing it, the energy, the amplitude of those oscillations rapidly increases. And that's it. That's all that's all that's happening. But the air fluttering was driving it at resonance. That's how that happens. That's the physical mechanism, and that's it. It's pretty straightforward. It's just whatever it is, wind, air fluttering, it's driving that bridge at resonance. So I'll let you watch it. I'll turn my sound off. It wouldn't suddenly collapse. All right, hopefully you've had enough time to watch the video. But there's a few takeaway messages there. One is that everything is not as rigid as you think it is. Just about anything under the right circumstances can behave like that bridge and be resonated and destroyed. For instance, I often tell students about a very large earthquake I was in Humboldt County, which is in Northern California, where I did my undergrad. And so there was a very large 7.0 earthquake off the coast. So it didn't really hurt anyone, but it was a small subduction quake, because a 7.0 is subduction quakes are usually what cause tsunamis, and big ones are like 8s and 9s. So a 7 is a fairly small subduction quake. But it looked like someone had picked up the ground and shook it like a blanket. And it didn't crumble and shatter, it just very, very nicely, moved like pulses, like a blanket. Sort of like that bridge. And it was very creepy because you could see it go all the way up to the mountain, just sort of because I was on a very flat area near the ocean. So you could see it go all the way through, and just everything just sort of plumped and went that way. This is one of the reasons why on the West Coast most houses are actually built on stilts, so that way that they can shift during an earthquake back and forth and have very little overall movement. So when you look at the bridge, I sort of feel bad there's no like really deep analysis, but that's how resonance works. All you have to do is find the resonance of your geometry, right? Every geometry has some resonant frequency associated with it. And all you have to do is drive at that frequency and you'll get collapse. That's it. That's all there is to it. Physics is sometimes elegantly simple. Actually, it usually is elegantly simple. It just can look very complicated. But of course, the math behind it, well, you'll notice we don't have equations for resonance. We just go straight to the end. I think they sort of look at resonance as an extra term on top of the differential equation. Well, not necessarily. Right, because you'd have to sync at the resonance frequency. If you're even a little bit off, you'll notice here, if you look at the graph, omega over omega d only occurs for a very narrow range. If you're even off a little bit, you aren't up here, and your amplitude drops off extremely rapidly. Yeah, well, whenever we straight ignore the equations, it's because they're hard. We have the driven term, and we can add that driven term to our system, basically, in a non-trivial way. All right, well, that is it for chapter 15. So it looks like we will cover chapter 14, but I don't see a reason to just jump into it today. Well, I guess we could do one of two things. I suppose, well, let me ask you something. So I was sort of struggling to find a day to review for the final. In my mind, chapter 14 is something I can always bring up in physics 2 the next time. And like I said, if you're worried about covering, I'm going to stop recording because I'm done with this.